All right, we'll get started here. All right, welcome to class. So, as I mentioned last week, today we'll be basically talking about the final exam. Just like the midterm, there'll be two parts of the final exam since this is a spatial programming course. There is a written in-class portion that will take place 2 weeks from today during normal class time. And we'll go over the content of that portion of the exam towards the end of the course, and then or towards the end of today. Then the other part of the take-home, or the other part of the class, will be a take-home assignment. Okay, so it'll be kind of like a culminating programming task that you'll be given that we'll go over now. We're actually going to talk about it. And that'll take the bulk of today's class meeting time, is talking about this assignment. Okay? We're going to make sure that you have all the tools for completing this assignment and that you understand 100% how to do the assignment. Let's see. I have up on the course website on GitHub, I have the a description of the final, when it is, and that sort of thing. And I'll also post a review sheet up on Canvas for the written portion, but it'll be a lot like the midterm in terms of the structure of the assignment. There'll be some code interpretation snippets. There will also be some logical, basically there'll be some information that you'll have to recall. And it will be open notes, open computers like the last one, so you'll have the opportunity to use the computer to figure out the answer. And that's to mimic how it works in the real world. You know, when you go out and get in a job, and you're asked to do a GIS task that involves programming, you'll be able to look up how you do things and how you get things done, what the right syntax is in order to solve that problem. That's the way I operate when I do research and work for other agencies. It is a great opportunity that we have to have the internet and have lots of information at our fingertips. So it will replicate that environment as you do it. All right, so what we're going to talk about today is that we're going to have this take-home portion, which will end up being half. So the take-home portion is going to be half of your grade for your final. Okay? The written portion, the code writing portion. And it's going to consist of you writing 2 scripts. So you're going to write 2 scripts, and one script is going to be a ArcGIS. You're going to implement it as an ArcGIS tool in a toolbox. So you need to turn in the toolbox, similar to about half of the labs in this course where you turned in a toolbox. And the other assignment is going to be you're going to write it and save it as a Jupyter Notebook and turn it into Jupyter Notebook. So we talked about both code styles in this course, and you'll have to do one of each for the final. All right, so we're going to go over the assignment. And as I go over the assignment, I'm going to teach a concept that you may or may not all be familiar with. Everybody that's sitting here should be familiar with both of these, but not everybody in the class is. And so I'm going to bring up a few PowerPoint slides in order to describe that. So we're going to talk a little bit about regression. Because basically, the first assignment that you're going to have to do is you're going to have to calculate lapse rate. You're going to calculate this concept of lapse rate, and you're going to have 2 data sets that I'm going to give you to work with and they represent a gridded raster of elevation and a gridded raster of temperature. Let me show you what I mean by that. So I'll open up ArcGIS Pro. You should understand that concept pretty well, or raster is, right? I would think. So I've created a project called Final Exam, but you can download this here in the course program for today. You can download this finaldata.zip, has all the data that you'll need to complete the final exam, and the data that I reference in the examples today. Okay. So I've downloaded this, and I've extracted the zip file. I've placed the zip file in my C temp directory, and so I have this finaldata.gdb file right here. And that file, that's a folder on disk, but ArcGIS sees that as a number of data sets. So inside of ArcGIS, I've added that database here by saying add database, and then I navigated to see temp, and I selected it, final exam, or finaldata.gdb. Okay, and then it's right there. What about this finalexam.gdb? That is the one that gets created automatically. It's always named the same as your project. So that doesn't have, well, it has a temporary data set that I created, but by default, if you were to do this, there wouldn't be anything there. Okay, so I'll emulate what you would see if you just opened up a project. All right. So I have a number of data sets, and I'll explain most of these data sets as I go through and explain the assignment and what you need to do. Okay. The first two data sets that we're going to talk about here are the, I'll go ahead and turn off the ones that we're not going to talk about. The first two data sets I'm going to talk about here are the USA elevation in meters. See that? That's what you're seeing here. What do the bright areas represent? If this represents elevation, by default, the bright areas represent what?
High elevation.
The high elevations, right? So does that look like it should look? We got high elevations out in the mountains, and got some lower but still high elevations here. What do we call these?
Appalachian Mountains.
What are the Appalachian Mountains, right? Exactly. Okay. So I'm going to turn this one off. This is the other data set. And this data set is the average temperature in June, the June average temperature. And so what do the brighter areas here represent?
Cold temperatures.
Right. So it's a raster data set. No, not cold temperature.
Colder temperatures.
Bright, the bright. Usually bright is
warm.
high. Yeah, so the warmer temperatures. Bright means warm. So these bright areas. So what is this bright area right here?
Hottest area.
Yeah, but in the United States, what's this? If I were to label this as by its state name, what would that be? Arizona. Yeah, I guess I might have been pointing to part of Nevada too, but yes, it's like the desert Southwest, so it's the hottest area in June, and we're right here. We're also still fairly warm, right? Okay, but what about these cold areas?
Rockies.
Yep, those are the mountains. Right? So we have a data set that represents elevation and a data set that represents temperature. And your assignment for the first part of the final exam is to calculate the lapse rate for a given area. So in other words, I want the user to be able to specify an area, and you need to calculate the lapse rate. Now that may not be something that you've heard about before. You guys, have you heard that term lapse rate before? But it's a very simple concept, right? So you might have heard about it before. You want to, or I'll just kind of, okay. So you've probably noticed as you go out into the world and maybe in your travels that, or maybe you just heard about it. As you go up in elevation, what happens to temperature?
Temperature goes, it get colder, right?
Yep, it gets colder typically, and we can see that relationship here, right? So we got the mountains, we turn these off, and up in the high mountaintops, we get a cold temperature, a cooler temperature. Even here in the Appalachians, it's cooler than the surrounding area. I went up to Tennessee recently, to Knoxville, to go to a football game back in October, and it was a little cooler up there than down here. Okay. By down, I don't mean southerly direction. I mean in elevation. But latitude also does have some effect on temperature as well. We know. All right. So what we need to do is find that relationship. And so lapse rate is defined as the average change in temperature given a change in elevation. And typically we talk about it being a rate. So for every 1,000 units of elevation that we go up, we get a temperature change. What's the average temperature change? Because it's going to change in different areas. There's going to be a different relationship. The lapse rate is going to be different in the Intermountain West than it would be, around here, or even up here in the northern Appalachian Mountains. Okay, so we've got that lapse rate will be different. What are some of the things that control lapse rate that you could think about as geographers? What might be some things that would change that relationship? In general, as you go up, it gets cooler. But what might change that relationship? I've kind of already talked about one.
The elevation, every time you go up, so distance between each point, the lapse. So if you have a lower elevation with a higher one, but that's not fact.
Well, yeah, so elevation, but how about latitude? Do you think latitude would also affect the temperature? Yeah.
How close it is to the ocean?
How close it is to the ocean, right? Because how close we are to the ocean affects another thing that's in the air. That's the water vapor. So it's actually one of the biggest. That's one of the highest contributors to lapse rate change. So when we see a lapse rate that's significantly different in one area than another, it's mostly due to humidity. Okay, to the amount of water vapor. What's that? Sorry.
Precipitation isn't part of it, just water vapor.
Yeah. Well, the amount of water in the air also influences the precipitation. So those would be two things that are related to each other. Okay. I know it's not a statistics class, but those would co-vary a lot. You see, in areas with high humidity, you also get lots of precipitation. Like right. So out here in Arizona, low humidity, low amount of precipitation. Here we have a fair bit of precipitation and a fair bit of humidity. Those aren't quantitative terms, fair bit, but yes. All right, so that's what we want to be able to do, is to calculate that lapse rate. Okay. So let's take a look at the assignment here again, and notice that actually the thing that I wanted to do here next. Well, before we get into that, what we want to do is to establish this relationship that says the temperature can be predicted by a change in elevation times a slope plus an intercept. So in other words, we want to establish a linear relationship between elevation and temperature at a specific location. Okay, that's our goal. Okay, this sort of activity is referred to as simple linear regression. Okay, and I do want to explain that term a little bit. So if you go back up, I have a short PowerPoint that I wanted to talk about. And you have to click on it and then say View Raw if you want a copy of the PowerPoint. I'm going to broadcast it here, so you don't have to download it if you don't want to, because you'll see it up on the screen. But if you wanted a copy of it, I did include it with today's material. Okay. All right, so this concept of building a mathematical relationship between two variables, the introduction of that concept is something that we often refer to as correlation. We say that two variables are correlated if they mathematically, if they change numerically. As one changes, the other one changes. So here's a simple example that I found in a textbook that I teach for another class, where we have the drug markets occurring in certain areas, and these are homicide locations. So we could say that the location of drug markets is related to the homicide locations, right? That's in a similar way to what we're trying to do. We're trying to say that change in elevation is related to change in temperature. One of the best ways to first examine a relationship between two variables like this, and in a GIS system, as geographers, we can look at their spatial position and make that the common thread. So we can take an observation and look at its spatial position, and then look at various attributes of that observation. So in our case, we could say the elevation here is, and the temperature here is, and we could do that for a number of locations, and we could create what's called a scatter plot. A scatter plot is a graphical representation of that relationship. So here is a scatter plot. Okay. So in our case, if we did elevation and temperature, or we did, what was the first example? Crimes and, drug locations and murder rates. So in other words, what we're saying is, if there's lots of drug activity, there's lots of drug activity going on, or vice versa. Correlation actually doesn't take a direction. Okay? But in general, we want to, in a scatter plot, we want to put the variable that we think that we're trying to predict. In other words, the variable that causes or that has a influence on another variable. So if we're saying that drug activity influences murder rate, then we put murder rate here. If we're saying that elevation influences temperature, we'd put temperature on this axis. So these represent all the locations and their value in the two different variables, elevation and temperature. Okay. So if our relationship looked like this in a scatter plot, we would call that a strong positive correlation. In other words, as elevation increases, temperature increases. Okay, is that true? Is that what we just talked about a few minutes ago? Does elevation, as elevation increases, does temperature actually increase?
No, it decreases.
It decreases. So it looks more like one of these three, this one, or this one. It should. Where as elevation increases, temperature should decrease. So the temperature values here are going down, the elevation values are going up. So we would refer to this as having a negative correlation. And its strength is how well it follows an average trend. How well it is, how well these values can be fit to a linear, a line relationship. In other words, can we predict elevation? Sorry, can we predict temperature? What the temperature should be based on what the elevation is, and that is correlation. All right, so we can have positive, we can have negative, or we could have a relationship that's totally random. No correlation would occur.
Well, Dr. Raven, don't you have to understand where you think the data should be before you can understand which spots you're going to take? If you don't understand that temperature go up, I mean, as you go up the elevation, temperature go down, if you don't know which one is which, you will pick the wrong correlation to go with.
Well, correlation is something that's derived mathematically. Okay, so we're not actually going to talk about the mathematics behind that, but yes, it is true that when you're trying to establish a relationship, you should have some scientific backing for that relationship. Having said that, correlation can also be a exploratory tool. In other words, we could look to find out if, in fact, two variables were related. We could do that in like socioeconomic data, like if we had census data. We could look at the relationship between something like, I don't know, we've got the number of, we've got educational attainment in census data. That's one of the variables that exists. So we could look at educational attainment and its relationship with any other variable. We could look at the presence of unemployment related to that. And we could see if those two variables are in fact related. On the surface, we may or may not have a reason for that. You know, we could read in literature and look at that sort of information, but we could see if those two variables were correlated. So today we're going to actually, we can do that right now. So this, if we go back here, I've created a small Python script called scatterexample.py. So if you download that and open it, I already have it downloaded. I'm going to open it up in IDLE. So here is IDLE. I tried to make the contrast better for you all to see with the black background. And what I've done here is I've imported NumPy, which is the module for doing what? What is NumPy useful for? We've used it before.
Numbers.
It's numerical Python, but its big new data structure that it introduces to Python is called what? That's something that like is an example of something that would be on the final exam. So a list. Okay, don't look at the next line of code. That doesn't really have anything to do with what I'm asking. So what's a Python list? It's a list in Python.
It's a list of items inside of a brand.
Right, and it can be, the items in a list can be any data type, right? So in NumPy, there's a new data type that's created that's kind of like a list, but in this data type, the elements of a blank, they all have to be of the same data type. An array, that's right. So an array is a data structure where all the elements are the same data type, and it takes up a chunk of memory in the computer. And so this module allows us to utilize NumPy and allows us to utilize arrays. Okay. And so I've showed you a few different ways over the course of the semester for creating arrays in Python, but here I'm going to create an array based on a random number. So it's going to generate a random number that is between, it's going to generate 50 random numbers. That's what this function does. So I generate 50 random numbers as an array. So X is an array and Y is an array. Okay. And then what's new this week? So we've done all this stuff before, and actually this line of code was just an experiment. Probably shouldn't have left that in. Yeah.
Do you get 50 different colors of that?
Well, you can use them to place labels on the plot. Yes. So that's what that's for. But I didn't mean to introduce that there. So what happened was that what happened is I create these two arrays, this X array and the Y array, and they're just filled with random numbers. And then I'm going to take those numbers and I'm going to run a function called polyfit. And what polyfit does is it attempts to draw the best mathematical fit between those two variables. So this could represent temperature and precipitation, but in this case it doesn't. It just represents these two random values. So you think the correlation is going to be very high between these two sets of random numbers, 50 random numbers? Is the correlation going to be very high between two sets of random numbers? It's getting hot in here.
No, it should be really low.
It should be really low, right? And what about the linear relationship? Should we have a linear relationship that looks like it's positive, negative, or just
Scattered.
yeah, it'll be scattered and the line will be relatively flat. Okay? And so I'm going to run this, and before I do, the other thing here is I'm going to calculate the correlation coefficient, which is that number between -1 and 1. So I'm going to run this, and there is the relationship that I got. So what do all these dots represent?
Okay, those are points. Well, you're trying to make them tight, right? You don't want them all over.
Well, I'm not trying to make them tight.
It's a scatter.
I'm just trying to plot where they are.
There's no correlation.
Right, there's very little correlation. There shouldn't be any if they're truly random. Okay? So each of these dots represent the value of X and the value of Y. That's what those represent. All right, and so yeah, this basically tells us nothing. Here's the correlation coefficient that was calculated, because I put a print statement in my code here. I printed the slope and the intercept of that line, and then I also printed the correlation. So this is the slope, and this is the intercept. The fact that these two are so close is just a mistake of randomness, really. If I ran this again, they would be different. Every time I run it, I'm going to get a new set of random numbers. So I run this again, and I get a new value. This time the correlation is positive, and we have a correlation coefficient value. This is the slope of that line, or this is the intercept, this is the slope, and this is the correlation coefficient. Okay. So if it's a positive correlation coefficient, the slope should be positive. If it's a negative correlation coefficient, the slope should be negative. And we see that here. Okay. All right. Now, what I wanted to show here is that if we had a real concrete example with real geographic data, we might see a scatter plot that looked like this. And this is one that we're actually going to run here in a second. We're going to talk about how to modify the code that I just ran in order to get a result like this. So in our scatter plot. So here the relationship is the latitude in decimal degrees is the x-axis, and the y-axis is the average date of the last spring frost. So what kind of relationship do you see here based on this slide? Is it a positive, negative, or no correlation? Yes, it's a positive correlation. So as latitude increases, what happens? What happens to the date of the last spring frost? Well, the temperature increases, but here we're not looking at temperature. We're looking at the average date of the last spring frost, which is related to temperature.
So
does the average date of the last spring frost go down? So as latitude gets larger, what is getting larger? It's not temperature. Temperature's not getting... So, you know, if I go to Canada right now, what's the temperature? Just is what?
So if you go to Canada, it's going to get colder right now.
Right, exactly. So that doesn't make any sense that this is temperature. It is kind of related to the temperature, right? Like the spring, what am I talking about? Maybe that's where we're having the trouble.
I guess it depends on what zone you're in and how you go up to a certain zone. But the temperature should be going.
Yeah, but in general, we're talking about the trend here. In general, as I go further north,
Right.
the average date of the last spring frost happens later in the year. Does that make sense?
So it's a seasonal change?
It's not really, I mean,
Is it based on it? Because the average spring frost change.
right.
And what is that bottom line there? I don't know what it is.
The bottom line here,
Yes.
latitude.
Okay, and is the latitude going up, going this way? I can't see it.
Yeah, so latitude increases in this direction. So it's conventional on a number line to have numbers get larger as you go this way or this way. So the latitude is increasing, and the average date of the last spring frost is increasing.
It's actually going up then.
Right. The average date of the last spring frost is going up as latitude increases. Does that make sense? Like as to why that would happen physically?
It's like moving from the south and going north Canada. It's gonna, well, I don't know if we're talking about temperature now, but that same changes as you go to higher level.
Right. We're not talking directly about temperature, but it's a concept that's related to temperature. So yeah, it's the average date of the last spring frost. So as I go up in latitude, the date that the last spring frost happens becomes later in the year.
Right.
So what this means is at 29 degrees, there's an observation that's at 29 degrees north where the last date of the spring frost is 50 days into the year.
Right.
That's actually not the smallest. There's an area that's at 30 and a half where the last day of spring frost occurs at like 47. All right.
Well, but that's not a kind of correlation. It's just one variable. This spring water plot is not as tight as it could be, but it is active.
Right. So that was part of my question that I asked earlier, and you're right. Like this relationship isn't as tight as it could be. Okay, there's probably other things that explain what's going on here besides just the relationship between latitude and spring frost. So, what's that? Like elevation. Good, right? And
but it is a factor because it is moving a certain direction, but you don't have all the elements to say this.
Yep.
But it is more like you said, positively.
Right. And so what we're going to do right now is use this code here and modify it based on what we've learned before to basically, instead of using these random x and y, we use some real data. So I have some real data. I have this real data with which to experiment with. So if I go back to ArcGIS Pro here for a second, that's what this question 2 features is. It is that data. So we have a bunch of weather stations that exist for portions of the southeastern United States. It actually doesn't go all the way over into Mississippi. Okay. And if I look at the attribute table, I can see that I have the average date of the last spring frost. That's what this column represents. And then I have the latitude right here. So I have the latitude and the average date of the last spring frost. So we want to take all of the values in this column and all of the values on this column and build a scatter plot as we have here, right? Except for our scatter plot now should have a tighter relationship that looks more like this, because this actually is that relationship. Okay. So that's what we want. That's what we want to do in code. Now this actually isn't the final exam question, but your final exam question is going to be utilizing a temperature and elevation. And in a similar way, you're going to have to create a scatter plot like this. So that's where we're going. So we're gonna practice doing it with a different data set, which is actually a feature data set, and you're gonna have to actually execute this using a raster data set. Okay. And you're gonna use two different variables. But the same concepts will apply. And the same you could utilize the same code, okay, because from this point down, this code is about taking two sets of numbers and seeing if they're related to each other. And so this code is about creating two sets of numbers, and that's the code that we need to change right now in order to get those two sets of numbers. So we could comment this out and say create two random values, or two random arrays. So we're going to clip that out. We don't need any of this. This area right here is actually the area of the plot. So we kind of do need that. That's kind of just setting something up. I'll actually move that up here. See, so what I mean by the area of the plot is how large this plot is going to be in inches when it's saved. So it's going to be 10 inches wide is what that's saying. And you could go read the help on plot. We talked about matplotlib before. You could go read the help on this function, and you can see that we're feeding the area in right here. All right. Okay. So now what we want to do, I want to add a new comment that says that we're going to read in a feature class. What's a feature class again? Right. So it's a GIS file that could contain points, lines, or polygons. So we're going to read in a feature class and choose two of the columns fields. That's just columns, fields. Those are interchangeable words when we use them to refer to GIS data. And then we're going to we're going to use correlation and regression to examine how they are related. So we're going to use correlation and regression to see how those two variables are related. So in our case, we're going to look at the average date of last spring frost and latitude. So what we need is an array that contains all of these values and another array that contains all of these values in the same order. In other words, the very first element in one array needs to be 85.27, and the very first element in another needs to be 36.02. They need to be in the same order. If they're not in the same order, it won't work, because regression looks number by number and plots each of these. So if they weren't in the same order, it wouldn't know how to create that plot. I'm going to show it on here. It wouldn't know what the pairs are. So it's just a one-to-one relationship. All right. Okay. So there are two different ways that we could investigate this or do this. Now, we covered one a lot better than the other, so I think that we should start with that way. And that way is that we're going to, well, I'll ask the question. If we want to take a shapefile and we want to build a new, well, let's leave that out for a second. If we want to take a shapefile or feature class and we want to go through row by row and examine the values in a particular variable, what kind of entity do we need to create? We did that earlier. We did that for like 3 weeks, just after the first exam. We talked about.
Can you say it one more time?
So we want to take a feature class, and we want to go row by row and pull out one of the values of a specific column. In other words, we want to go row by row and pull out these values, 85.27, then 96, then 93, 22, and so on. It's not an ArcGIS tool, okay? It's
We want to split it, right? By the, no, I can't think of the name of it, but I think I know what you're talking about.
Well, if I was doing it Excel, it would be a lookup function. I say look up this and give me the values. Right?
okay.
Do you create a loop that has a certain condition?
We got to create a loop, right? That is true.
Cursor.
How do we, a cursor, yes. So we could use a search cursor to allow us to loop through all of the records and pull out just this value. Right? And actually we could use it, we could use to pull out 2 values or whatnot, right? Okay, so that's exactly right. That's what I was thinking of, a search cursor. Alternatively, we could either turn it into a NumPy array, or we could turn the whole data set into a pandas data frame, which we didn't get a whole lot of chance to cover in this class. We talked about it last week. So we could turn it into a NumPy array or a pandas data frame, and then just ask for just that column. So I'm going to demonstrate or talk about each one of those because they're each valid. It would be interesting to see which one runs faster. The one that runs on the one that turns it into a NumPy array is going to take less code. Okay, so there is that to consider. But neither one's going to take a whole lot of code. So let's do that real quick. So the way that I would solve this problem is to refresh my memory. Okay, so I know that I need to use a search cursor, and you guys correctly identified that after a few minutes. So how do I create a search cursor? Well, I think I could punch out the syntax, but it's always helpful to search for it. So we know we're going to use ArcPy, which is the Python module for interacting with ArcGIS data. Then we could say ArcPy and then say search cursor. So we can look at the help in this way. I like how now it defaults to the ArcGIS Pro help. But before, when it didn't, I would also include ArcGIS Pro in my search. So just like all the help in ArcGIS Pro, there is an example. Okay, so there's a few examples of how to do a search cursor here. And all these use this with syntax, which we can use. Oh, here, this one doesn't use the with syntax. Okay. This one actually does a sort. All right, so let's see if this one does. Nope. Yeah. Okay, so I'm going to take. I'll just take this last. This last one seems fairly simple. This last example here is going to. If we read this example, it's taking a feature class and it's pulling out these 2 fields. That's kind of nice because we're actually going to be pulling out 2 fields. So I kind of like that help, this one. So I'm going to copy this help one and copy this over. and put it into our script. And by the way, I think I'm going to save this script now so that you'll be able to see it when I post it on GitHub. I'll say this scatter example from data, from GIS data. I don't like to put spaces, so I'll say. I'll just call it GIS data. All right. So now we have that. So instead of getting these two random arrays from here, we're going to get these two random arrays. They won't be random anymore. We're going to get them out of this data. All right. So what do we need to change this line to? What's this line doing? So what's a plain English?
It's telling you where the data is at.
Right. It's referencing the data on disk. And so we need to figure out where our data is on disk. And yours will be different on your computer. So be careful with that. So what we're going to do here is if I right click inside here, I can look at the path. It's ctemp finaldata.gdb. So I need to pull that over. And then I say slash, what was the name of it? Question 2 features. Question 2 features, and that should be good. All right. Now I have to put a little R over here. Anybody know why? I've explained that a few times, but it's not like vital. Yeah, go ahead. It disregards any special characters. So in Python, a backslash going this way is a special character that means that the next character, it's funny because it's a special character that means that if the next character is a special character, ignore it. So that's what it means. And so doing that messes it up. So you have two options. You see in the example that they posted, the ESRI posted, which was right here, they switched the slashes to the other direction. You can do that, or you just put an R in front of it. I personally, my code style, I like to put the R in front of it. That just means ignore special characters. I don't have any special characters in there for you to deal with, so just treat it like a regular string. I don't know if that's for sure what the R stands for, but that's the effect that it has. Okay, so what data type is being created in this? What data type is being created in that line of code? Do I need to make this a little bit bigger? Oh.
Word will be data streams, right?
Well ID and well type are strings. That's correct, but they're being put into some larger data type. What's that?
Yeah.
A list.
A list, right? Exactly. So the reason that we need to create this list is that our search cursor can contain all the fields that are in the feature class, which we can just put a star, or it can contain a list. And our search cursor will only contain those items in the list, or those fields in the list, or sorry, fields, those columns in the list, right? So what do we need to put if we want to get out the two fields that we want? What do we need to change these to?
Whatever the fields are in the ARC row.
Yes, whatever the fields are named. So we need the average DLS PF. Average, I think it's capitalized like that, yeah. DLS PF. And then, oh, sorry, go ahead.
So you can just information from the attribute table, you know, just fill it out, the data that you need.
Right. Now, if you were trying to generalize this to work on any data set, you could just change fields to a simple string that just had a star in it. Remember? And what would that do?
Star would give you every item.
It would give you all the fields. So that's like ArcGIS's terminology for just all the fields. And you could get all the fields, you could print them out, you could examine them, and then you could choose the fields that you wanted. You could even ask the user, like, you could write your script so that it listed the fields and then it told the user, please type the fields you want to use. Remember we did that like way back at the beginning of the semester. You could type in the name of a field and then you could proceed on with your code.
Okay.
All right, so the average date of the last spring frost, and for now we're going to do the latitude. So now we're going to get those two fields. Now in this example, let's look. So it's creating this this arcpy.da.search cursor. That's where it's creating the search cursor. So let's go look back in the help, because I don't know if we need all of the parameters that we're feeding it here. I don't think we need this one. Let's go refresh our mind on what that means. So we go back over here and we look at, in the help, we look at, for a search cursor, we can see that the first parameter that it asks for is the in table. The in table is the feature class that we're going to use. It's the one that has the tabular data that we're trying to manipulate. Okay? So it has that. The second is the field names. Did we already establish what field names we wanted to use?
Yeah.
Yeah. What field names are we using?
Average date of last spring frost and latitude.
Yep. All right. In the help, what do these curly brackets mean? They don't mean dictionaries. Like,
It means optional, doesn't it?
right. It means optional. And so what we're doing here is we're saying that ESRI is saying that all these other things are, just bit my tongue. All the other things are optional. So what's the other one that we're providing in the example here? It's the SQL clause. So it's this one. So the SQL clause will allow us to, like, it looks like it says organize the data, maybe sort it, make it distinct or group by. We don't really want to do that. We want all the data, and we don't really care how it's sorted as long as we get the same relationship. So that's what I was saying right here. We know that we can just take this out. We don't need it. So we're just, oh, you guys went black for a second. Let's just turn the lights off.
Yeah.
Okay. Would it help if I was trying to get the text a little bigger? Options, format. I made it black because last week we were talking about how it was all washed out. There should be a way to make the size a little bit bigger. 16, 20. Okay. All right, that's a little bit bigger text. I'll make this take up the whole page. All right, does that look a little bit better? Maybe. All right, I'm gonna remove this comment because it doesn't really have anything to do with it, especially since we took the SQL statement. All right, so this row is going to, this cursor is going to create an object called row, and it's going to do what? We already said the example. It's going to loop. It's going to loop through all of the data, and then the only thing that's inside of the loop is right now we're printing out the value in this column and the value in the latitude column. So I'm going to run this guy, and you'll see that we get that. It's still going to do the whole. It's actually going to die because we no longer created the X and the Y that we did before. But do you see how now we have these values, 8527, 3602, and those should be the same numbers that are in here. 8527, 3602, 96, and then 37, yeah. So see how those are the same numbers?
Right.
So we've gone through and we've created a loop, and the loop is allowing us to access those values. So what we want to do is if we want to leave all of this code the same, we can create a new thing called X and a new thing called Y. A new thing called x and a new thing called y, and we need to put values into x and into y as part of the loop. So first of all, let's talk about what data type do we want x and y to be? What data type were they before in the example?
Loop.
No, the data type of the whole thing. It's a sequence.
Oh, list.
Yeah, so, well, they were arrays, okay? But Python will treat arrays and lists the same, okay? The only thing is that arrays are more efficient. So with big data, you want to use arrays. But with small data like this, we can create lists. So you're right, Ashley. We want to actually make these lists. Lists are efficient because we can add things to them, where arrays, you can't grow the size of an array. You can modify values in an array, so it is mutable, but you can't grow the size of an array efficiently. There's a method for growing the size of a list, for adding a new item to a list. So we're going to, yeah, go ahead.
What's the difference in, okay, you just ran the one there with averages and latitude. Now you're going to go back and go with X and Y. So you can run more than one, two fields at a time, everything to come up with the correlation, don't you know? Every one you add an X and Y to it.
I'm going to put a little comment here that I think will answer your question. Store all the average day of last spring frost data, and this list is going to store all the latitude data as a list. Okay. So the only reason that I named them X and Y is so that I could reuse this code without changing every time I used X and Y down here, right? So these will represent the, it's mathematical convention actually to call the predicting variables X and the response variable Y. It's just a mathematical convention that I'm choosing to follow here. And so I'm trying to predict the average date of last spring frost based on the latitude. And so I'm going to make latitude be the X, which is the predictor variable, and the response variable Y is going to be the average date of last spring frost. So I want to make these lists. How do I make a new empty list in Python again?
Just clear it out.
Just leave the brackets empty. That's right. So I've created two brand new empty lists, right? And so we've already established that row 0 here. I'm going to modify this print statement a little bit. So instead of using a print statement, I'm just going to say row 0 is the value for this row of the average date of the last spring frost. And then this is the value for this row of latitude. All right, so what's going to do is it's going to loop through here, and row bracket 0 bracket is going to be equal to this value. And I want to put that value into this array, X. I want to put it in there. So what's the function that we learned about for adding a value to a list? Update cursor will take that value and put it into another cursor. So that's good, but it's not correct here. Here I'm just trying to take a list that's empty, and well, it's going to be empty at first, but every time through the loop, I want to take a value and stick it into the list. So row 0 is always changing. Every time through the loop, I get a different value. I want to take that value and shove it into X.
They return value? No.
Okay, so what I would do here is, I know the answer, but add an item to or add a value, maybe. A value to a list in Python. How do I do that? Oh, there's actually a few different ways. Do any of these sound familiar that we talked about?
Insert pin.
Yeah, append. Append is one that we talked about a lot in this course. Insert will allow you to just like stick it anywhere. But we don't really care about sticking in a specific place. We want to stick it at the end of the list. That's what append does. So if we say x.append, actually, I'm doing that wrong, right? I want it to be that y.append, and this to be x.append. In other words, I want the value that's in the first column to go into, the second column to go into x, because that's latitude. And I want the value in the first column to go into y, because that's the average date of last spring frost. So the value that is in there will go through each time. So now I'm going to run this. And
GHY. And on that portion before, don't you got to change those field names, Dr. Ray? You still got the same old field names, that field names. Don't you have to change those?
What old field names?
At the top, in that formula thing up there, you say LC equals field. Is that still part of this thing?
These are the field names I'm using: the average date of the last spring frost and latitude.
Just talking about in the loop for row and archive.
Well, we run this thing again, and you can still keep that same data up there. You can still keep that average and all that other stuff, because we're not trying to find that out, right?
Sorry, like what?
Oh, okay. So you say append the values. See, you say when I append the value to row A and B. Are you doing it, or is that's all still part of this?
Yeah. Yeah, we're still doing that. See, look, now I'm going to print X and Y. I'm going to run this and show you what's in there. So now X and Y, it's still going to fail because I one more step I need to do. Okay, so look, here is, I don't know where X stops and where Y stops, but here's all the values in X. See how they're 36.02, 37.3, 35.88. See, if I look here, I'm going down the row, 3602, 37.8, 35.88. See that? Oh, here's where the other one starts. I'm going to put I'm going to do this again, but I'll say print X, and then print Y, and then print. So I just put a little marker in between. Forgot the parenthesis. See that? So now I have a list where I have all of my values. See, these are all the values for latitude, and these are all the values for the average date of the last spring frost. I have two lists. These are going to be my X and my Y now. Does that make sense?
So you're always looking for X and Y, just doing this particular thing. You just happen to be doing X and Y this time, but
yeah, but I could call these I could still call them something else if I wanted to. This is just still just a variable. But yes, I always have two for doing regression. I always have a prediction and a response, or a correlation. I always have a prediction and a response. So I could call this prediction and response. I don't spell predict, right? Okay. X, Y. In fact, because these are lists, I'm going to call them X list and Y list real quick. So what I've done is I've asked for a search cursor for all of the data, okay? And then I've gone through and I've built a list that contains just the values for average date of last spring frost and just the values for latitude. And they're in the same order. I know they're in the same order because I built them in the same order here. I appended them the same order. So the last thing for me to do, the only thing left for me to do here is to convert the lists to NumPy arrays. So I need to convert the list that I made into NumPy arrays, and I could do that pretty easily. But if I didn't know how to do that, I could say convert a list to a NumPy array. NumPy.asArray, and they've even got an example. So here, put two of these, X list, Y list, and then X.
Do you need to import NumPy first?
I created the that's a very good observation. But when I was creating those random arrays, I was using NumPy already. So you're right, I would if I hadn't, but I did. So, all right. So now this will run. And there is the relationship. And that plot should look really similar to this plot. So that plot and that plot, they look the same. The axes are a little bit different. The axes are labeled a little bit different, and the min and the max is a little bit different. But you can see these 2 points down here are those 2 points. So it's this one's a little more stretched out along the bottom, but that's the same. Okay.
So it only start plotting when you change it to a NumPy array. So it continue on with the program once you change the data to NumPy array. Is that correct? Because you read it before and no plot came up.
Right. Well, this function right here requires 2 NumPy arrays, and so does this function right here. Requires that you give it 2 NumPy arrays.
And when you put that NumPy as array list in there, it converted whatever your output data to a NumPy array so that it can execute that plot.
Right.
Correct?
Yep. So at this point right here, we had two arrays, just like we had at the same point here.
Will it not run if it's open in ArcMap?
It should still run if it's open in ArcMap.
And you still have the NumPy, the X equals NumPy random and stuff like that up top. That's still commented out.
I just have it commented out, yeah.
Okay.
So when you make that other thing, was that going to take the place of the random number, what the reason why you, okay, the reason why you comment them out because they random numbers. You don't need that.
Yeah, I first showed it with random numbers, and then I showed it with some real numbers.
Okay.
What do you think? Too hot in here? I'm getting hot. I'm not going to lower it too much, but I'm lowering it down to 72 from 74.
Looks like I'm wearing this sort of sweater.
I was wearing a sweater and I shed that. All right, so go ahead.
So Dr. Rachel, when we get ready to do that final project, you're just showing us now how to take two items, two X and Y's or X, Y list to do this what you just showed.
Right. So you could, what you need to do for the final project, for the final exam, the first number, and we're actually gonna do one more example that's gonna take you even closer to it. Okay. So this right here is meant mostly to teach you about regression and how it works, and then we'll have one more example that'll take you one step closer to the final exam. But yeah, exactly. So the X and the Y here are the values that you need to get. And then you'll get the slope of the intercept.
And that regression PowerPoint's on the meeting 11, right? Is that the same PowerPoint we used to do every time?
It is the same PowerPoint, but it's up there. It's not the exact same PowerPoint. It's like it's a lot less. So I just need you to kind of have in order to do this assignment, I need you to kind of have a general sense of what regression is, and so I included that. It's pared way down. So I'm going to go back to that PowerPoint just for a minute here to finish this off. So the correlation coefficient, we've talked about that. It's ranging from 1 to -1. And so now when we run this, here's our correlation coefficient for this data. It's 0.85. Does that mean that it's positive, negative, or no relationship? Positive. And it's pretty strong. I mean, 1 is the very strongest. So it's not like it's like super strong, but it's pretty strong. And then this is the slope of the line. So what that means is that for every 1 degree in latitude, we see a 7-day later spring frost on average. So that's what that tells us. I mean, that's kind of like the important thing in the model. Like, if we were to make a mathematical model and we were trying to describe to somebody, hey, well, in the southeastern United States, on average, a 1 degree change in latitude means that the spring frost gets there 7 days later. That's kind of like the story of this relationship. This value isn't so important. So this value is the intercept. In other words, if latitude was 0, where we would expect the average date of the last spring frost to happen. So in other words, at latitude 0, at the equator, we would expect the average date of the last spring frost to occur at -151 days. Does that even make sense?
No.
No. So that's another thing about regression that we often say is that it really only operates over the domain that you've tested. You're extrapolating if you go beyond that.
Yeah, because there will be a spring frost in
Right. There wouldn't be a spring frost. Yep. The physical process that's controlling this doesn't even apply to there.
So, I'm looking at the code, and that's pretty much just a line formula then, like the M and the V at the very end of that. So like 7.1 is essentially the slope of the line, right?
Yes, exactly. Yep. In fact, what this line of code is doing is actually putting a line on the plot at, and this is the function of the line. So M becomes the slope, X becomes the value, and B is the intercept. Of course, it's off the plot, but it's still it still needs to be it's still necessary for the slope of the line. Now, something I haven't shown you before is that you can save this or show it. You can't do both. So I'm going to run this one more time where I comment out the plot.show and I uncomment this plot.savefig. And when I do that, I'm going to save the figure to a specific location. So now I go to C temp and I save the name of plot.png. So there it is. So
program alone, it's not intercepting with ArcGIS or Pro. You can run this totally outside of that, right?
So ArcPy is allowing you to run the code that ArcGIS Pro has installed. So this code would not work without ArcGIS Pro installed because you wouldn't be able to import ArcPy right here. I'm going to go ahead and move this up.
So we have to work in conjunction with Pro.
Right. Now there are libraries that work in very similar ways that work on GIS data that are open source. I think I mentioned some of those last week, but Shape.
Pro has to be open when you running that, or it just running by itself?
No, ArcPro does not have to be open though.
Okay, so you're not Pro at all. You're just running the script.
Yes. Yep.
Okay.
Just running the script. Right. Okay. All right. Now I told you I promised you that I also do this as an MP array real quick. So I'm gonna file save, and then file save as, and I'm gonna rename this just GIS data. Oops. GIS data 2. Okay. So rather than here, I'm going to delete all of this data. Yep. And what I'm going to do is look up feature class to numpy array.
So we're doing the same thing, just with the numpy array, right?
Right. And so I'm going to look at the example here. So what it wants is it's going to give me an array using arcpy.da.feature class. I'm going to feed it the same feature class, and I'm going to feed it the same fields. And what I'm going to get is a what they call a structured array that has both of those values in it. And then I could say that x is equal to ARR latitude. Actually, a better way to do this would be fields 0, and y is equal to ARR fields 1. So this is basically taking, y is going to be, it's going to be 1 and 0. Again, because x is the latitude, the one on the x-axis. And so this should just run unless I've done something wrong. Oh, it just saved it out. So let's change this back to show. Yeah.
Look, GIS, on in order to pull the information off the attribute table, right? You said it has to be on. You pull that data from the table. Put the X and Y from the table, right?
Right, but like ArcGIS Pro doesn't need. ArcGIS Pro is pulling the data out of the file too. Like this data isn't in ArcGIS Pro; it's in the feature class.
Oh, okay. So, but in order for you to see the feature class, it'd be easy to turn on our Pro and look at it.
Yeah, I'm just using ArcGIS Pro as a tool for allowing me to inspect the data and see what values are inside of it.
Okay.
Yeah. And in fact, let's say because I forget what I think it was Ben that said elevation might be related also to the average date of last spring frost, right? So how could I change this? So instead of latitude, I was going to use elevation and look at its relationship.
Okay.
Change latitude to the
Oh.
elevation field.
Elevation. So now I run this guy, and I can see the relationship between elevation and the last day of spring frost. Now, does that relationship look as strong?
It does. It's positive, right? But it's not as scattered. Right?
It is positive, but it's more scattered.
Uh-huh.
Yeah, and look at the correlation coefficient.
599.
Oh,
Yeah.
It's kind of low.
It's almost.
So what's the cutoff, Dr. Ray? Which way you try to get as close to? You don't really know what's going to be the variable that make it really tight, so you just experiment.
Right.
The higher the decimal gets towards 1, so 0.98, 0.87, those are really strong. And the closer it gets to 0 means it's weaker. So,
but it's only going to find out a number ahead, so then you might have to keep searching for other variables to try to get it tighter.
oh yeah.
Is that right, Dr. Ray?
Yeah. So, in this class, we're not going to take it any further than where we are. But yes, you could have multiple variables that explain it. But this class, we're just showing the regression equation as an exploratory technique. Okay. So yeah, it's weaker, and then this is the slope. So what that means is for every unit change in elevation, the average day of the last spring frost changes 1/100th of a day. So every time I go up, I believe the elevation units are in meters. So every time I go up in elevation 1 meter, the average date of the last spring frost should occur 1/100th of a day later. That's what that slope is saying. So
once you have this set up, it's really easy to change variables. You just switch out the field name at that point, right?
right, exactly.
Okay.
All right, so let's go back to the assignment. So that's just doing it a different way using feature class on UMPy array versus that. We could also do it as a panda array, but if we did it as pandas, we have to import the ArcGIS library because ArcPy doesn't have a method for converting to pandas. Only that ArcGIS library that we talked about last week has that. Okay. All right. So what we want to do is we want to build a tool that allows a user to specify an area and then extracts an array out of the raster, the temperature raster and the elevation raster, and builds the same concept, builds the same chart and does that sort of thing. Okay. All right. So I do have a starter script for you that does a lot of this. So I'm going to go File, Open. We'll talk about this starter script.
And this is the actual starter script for our
Right.
final.
For final.
Take home. Recording.
Yep. So this is the starter script for the take-home portion of the exam. For script 1. For script 1. Okay. So for script 1, in the end, one of the things that you're going to have to do by yourself is work this into a toolbox. Now, the toolbox part of it. So here, well, actually, let's talk about the toolbox part after we talk about building it. Okay. But if you go back and look at the requirements, you'll need to specify a feature class that will form the boundary of where you're going to look at lapse rate. So for example, let me zoom back out here. So I have included 3 samples and an irregular sample. Okay. There's my irregular sample. I don't know what that looks like. But I've included, that's just a, we're actually going to talk about why I included that here in a second. But here's my 3 samples. I have a sample here in Washington, a sample here in Arizona, and a sample over here in Western North Carolina. So those are the 3, I'm going to turn this off because it's not necessary anymore. So those are the 3 samples I have. And then ideally you need to write this script so that the user could provide any polygon, and that's why I included the irregular polygon. So you would want them to be able to do it anywhere within the bounds of this data. So obviously I'm not talking, you can't do it in Australia because there's no elevation and temperature data over there. Okay. All right, so what the starter script does is it creates a variable that references the location of the sample. Now in reality, your toolbox needs to specify where on disk the sample is. So your toolbox needs to reference this location. So it'll be passed and received using a get parameters as text. So that's how you get that, just like on the first exam, first take-home exam. The second one is an output location to save the raster out. And so the user needs to be able to specify where to save the resulting raster. And by the way, I have the correct answer for the 3 sample areas. So in other words, if I'm going to add this to it, so that was sample 1. So if I turn off sample 1 here and I zoom in, that's the correct answer. That's what you should turn in for raster number 1. And then, and so on. You're not actually going to turn that in, but that's the way your script should produce that. And that's one example of how to get the right answer. What are these little things right here? What's that? Yeah, those dark spots are mountaintops. Exactly. Yep. So what happened up here in the Pacific Northwest to create those kind of like round dark spots? What's that? Well, this is temperature. Yeah, this is temperature that we're seeing here.
So the dark spots are cooler places, right? So it might
Right.
be depressions in the mountain tops.
Yeah, what I was specifically looking at is why are they shaped like that? So I didn't ask the question very well. But this is Rainier, and I don't know what the name of these two others are, but those guys are volcanoes. Some extinct, some not. But that's why they're shaped like, you know, that in the end. Okay, so we've got our precipitation and temperature, and what this script does so far, it actually gets you pretty far in the process. All right. So
can I ask a quick question?
Sure.
You said you wanted us to let the user specify the output.
The output location.
Output location.
Yeah. So here I've specified a location, but I want to let the user specify it.
Okay.
So in other words, it needs to be a parameter in the toolbox, and we'll talk about setting the toolbox up. And I'll actually upload a starter toolbox too. I'll do that when we talk about it. Sound good?
Mm-hmm.
Okay. So okay, yeah, so here is the study area, there's the output. The output is going to be it's going to be a raster that contains a temperature value that's the model temperature value. In other words, for a given elevation, it's going to be the temperature that it should be if it followed that straight line path. Not the actual temperature, but the model temperature. Okay? So you're going to build it. Once you get you're going to get an equation that says slope times elevation plus the intercept equals the model temperature. All right. So here you're going to set up the input rasters. The input rasters, you're going to leave this the same. Yeah, go ahead.
Can you use your mic, the next mic with the mouse?
Yeah. So these two lines of code, the only change you're going to make is where your data is saved on disk. You're not going to allow the user to choose the elevation and the temperature data sets. You're going to use the data I've provided you, and you're going to hard code it into the toolbox. So all you need to do is change where you're going to put them. If you want to put your data in ctemp final data, you don't have to change these two lines of code. If you extract your final data.gdb and put it in that directory, you won't have to change those two lines of code. Okay. All right. Now, we talked about environmental variables last time. What these two environmental variables do is set the mask and the extent. Anybody take a guess on to why or what they do? What does it do when I set the extent? When I run a tool and I have an extent set, what's the result going to look like?
That's like this, I hate to say it, that's like the study area, right? That's how big of a section you're looking at.
Right. So anytime I execute a tool, the result, even if the result should be larger, it's going to be limited in size to just whatever is in the study area. So what it does is it has the effect of clipping to a rectangle that is the same extent as whatever the extent data set is. Okay. All right. Now mask is actually really similar. So if I didn't know what it did and I wanted to find out what it did, I would go arcgis or arcpy mask env.mask. There we go. So here, if I run a tool and I have a mask, the result will only exist inside of the mask. So clips it to a the extent makes it a certain rectangle size, and the mask makes it so that it only exists within that shape or that polygon, depending on whether you're using a raster or a vector for your mask.
So the extent has to be a square or a rectangle of some sort. It can't be irregularly shaped like mask can.
Well, a better way to say it is whatever you provide as the extent, it will become a rectangle. See, I still provided the study area here, and even if it's not shaped as a rectangle, it will make the minimum bounding rectangle around it, and it will decide that that's the extent. Does that make sense?
Mass look like a dissolve on that feature, well, no, but it's not that, is it?
No, that's not really a dissolve. A dissolve is a tool. This is an environment that will change the way it's processed. Here, I'll run it manually. So the reason that we're doing this is so that I can clip out just that portion of the data set. So right now, what does this code do? Sorry, I'll go over here. What does this code do? What does the times tool do in ArcGIS? Yeah, so it's going to take temp raster, and it's going to take every single value in temp raster, and it's going to multiply it by 1. Right? Why would I do that? What's the result of multiplying everything by 1?
Making a copy?
I'm making a copy, right? But that copy is going to be influenced by the mask and the extent settings.
Would that be so that if there's an area that doesn't have any data, then it has data? No, it wouldn't work because
That's going to be, we are going to do that. That's going to be in a second, though.
Or they're making a copy at the size of the extent.
Right, we're making a copy that's the right size. So I'll show you what this is doing. In code, this is what it's doing. Not in code, this is the equivalent. So if I went over to, oops, I don't know where I'm geoprocessing that. Okay, so I'm going to go to Tools, and then I'm going to go to Times.
Isn't it changing the size, so that it doesn't change?
Right. So I'm going to take here in this code right now, I'm taking the temperature raster and I'm multiplying it by 1. So I take the temperature raster and I'm multiplying it by 1.0. And this is going to be my output data set. I'm not going to change that name. Okay. Now if I do this, I'm going to get the exact same data set. Like, I'll run this, and you'll see that I'll get a humongous data set that is the temperature raster again. So now I have a copy of the temperature raster. It is exactly the same, because when you multiply any value by 1, you get the same. So these two rasters right here are the same raster. Okay. But that's not what I want. I want a copy. So what I want to do is change the extent to be the same as my sample, and I want my mask to be the same as sample 1. Now I'm going to rerun this, and what it's going to do is instead of copying the entire raster, it's going to copy just that value right there. Now you say, it looks different, right? Like, do they look the same anymore? Why is one lighter than the other?
Is it because it's in relation only to that square? So like the
Yes.
zero starts different spots?
That's exactly why. So if I click on one of these values for, here, let me get, there's got to be a way to get, there's got to be a way to get the information for all of the.
I did that on there.
In ArcMap, you have to tell it whether you want all visible layers or just the top layer, and I don't know where that exists anymore. Here, I'll just zoom in like really close so I can tell. So I'm going to hit this one right here. That value is 9.80. If I turn off, that one is 9.80 to hit the same one. See that?
So it's the same value, it's just colored a little differently because of where the white starts.
Right. Yep. It's the same value. It just the white is what it is the color ramp has been applied to the min and the max. You can change the color ramp by looking at the symbology, and say, okay, I want to do min max, and I want to set the min to be 0 and the max to be 20, and then that'll do that. And then I could do the same thing to this one if I wanted to. So I go into this data set and set the min max, and then use the custom range and set the 0 to be the min, the max to be 20, and then I should get the exact same. Yeah, see, get the exact same color range. Right? So there's a little bit of a shift, but I can't when I turn them on and off, you can't see the difference that well. Okay. So they're the exact same data set. Now you could say, well, you could, instead of doing this, you could just clip the raster out, and that's fine. If you wanted to do it that way, it would work. There is a tool for clip raster. You'd still want to set the mask though, because the mask would actually clip it to the polygon if the polygon wasn't regular. In our case, the polygon is regular, so you don't really need it, but I do have that included raster. In fact, let's do this one more time. So if I go to geoprocessing and I change the extent to irregular, and then I change the mask to irregular. I'm going to run this guy. Irregular was over here. So there's irregular. I'm also going to change this symbology back to the data set. All right, so there's irregular. And if I had not set the mask, it wouldn't be cut to the irregularly shaped polygon. See this? That's the irregular shaped polygon. And then I've extracted temperature out of that irregularly shaped polygon. Does that make sense? And there's so little temperature variation there in that region. You can't see it very well, but when we stretch it to only include the range of this area, you can see that on some scale there really is a difference in temperature. It's kind of interesting.
If you back out all of that, will you still have the same small square up in the top, the western part of the United States, because you just changed? You don't have it anymore, right? The square gone.
No, I wrote over it to create this one.
What I'm saying is, if you don't write it in like that, it won't be there. So you're just trying to narrow the scope of what you look at and study.
Yeah. So yeah, I was just showing it. I'm making another example of why I'm doing this in the code.
Okay.
All right. I was just saying that it's totally necessary to have the mask in there. So since the mask is already necessary, it's easier to just use the extent variable rather than using clip raster as the tool. So instead of using clip raster, I just use times. It's like a shortcut. All right.
So which one, I think, are they just things, which one we use to do the program? Like you saying, we just people want to.
Yeah, I mean, in the end, you can do it however you want to do it, but
Where does it come up with that picture you told us? So in order to come up with that picture of what you're talking about,
yeah,
we would have to do it the way you showed us before you can get your regular stuff, correct?
right. Okay, so here, the next step that I'm doing already for you is I'm taking the temp area. What is this, by the way? Temp area and elev area at this point. After we run this, what's that? Those are raster data sets, exactly. So we're converting those raster data sets from being raster data sets into NumPy arrays right here. So I'm taking the data sets, I'm converting them to NumPy arrays, and I'm converting the no data value into -999. So whatever no data value was there, anything that's no data gets the value -999. And the reason why I did that is, what if the user chooses an area like out over the ocean and some of it includes the ocean? Or what if they draw an irregularly shaped polygon? Are there any no datas in this raster? This raster right here, are there any no datas?
In the irregular shaped one?
Yeah.
No.
Yep, there actually are. All rasters have to be a square. And so here, I'm going to display no data as red and show you that. Oops.
And then you did it on the big one. So
I did it on the big one. So I'm going to display no data as red, and you'll see that.
there's a little lot.
Yeah, in fact, I don't know why that. I think I confused it by. So I must have made the extent the same as both. Like it added both of those.
Right.
But if I run this in code, it won't get confused like that. So in any case, you definitely have no data values right here and right here and right here and right here.
So
See?
any irregularly shaped raster has no data values.
Right. A raster has to be a square.
Square.
So the reason that I did that was I wanted to make the no data values a value that I could deal with. Okay. Now, flatten is a function that will take a two-dimensional array and turn it into a one-dimensional array. So it doesn't really matter to us if it's a two-dimensional or one-dimensional, but it matters to the regression equation data set. Okay. I mean, to the regression equation function. All right. So the last thing that I do is I go find, what this does is it creates a new data set called X, and it takes all of the values, it finds all the values that are greater than -999. So in other words, it finds all the no data values. I think that it might be a little bit more clear if I do this in two steps. So instead of calling this X, I'm going to call this good index, let's say. So this is a list of all of the no datas. So that's why I'm calling it good index. Right? And then I'm going to change this to X equals the temperature was temperature is going to be Y. do that in a second. Second. Okay. So what this is, now this is creating my X and my Y arrays that I need to feed into the other code that will create the data sets that I need to create. Okay. So X and Y. So at this point, I need to go everything below here. Okay. I need to write some new code, which we'll talk about in a second, and I also need to pull the code in from the other from the other Python example that will build a scatter plot from the X and the Y data. So, but I have my X and my Y data. Yeah, go ahead.
I have a quick question. See where you made good index, that's only choosing the temperature raster. So would you need to do two of those, one for the elevation and one for the temperature?
You definitely would in a normal case, but the data that I'm giving you, so that's a good question. The data that I'm giving you, and in reality, you probably want your data like this. Otherwise, it would be really hard to keep track of. But the data that I'm giving you is already, so this USA temperature grid and the USA elevation grid is already the exact same size, and so it will have no data in the exact same place. It's the exact same size with the exact same cells. So first of all, that was a great question. But so this line of code gets the indexes to all of the good cells in the raster, and this one says, okay, the good cells in the raster are going to be into a new array called X. And the good cells in this raster are going to be in a new array called Y.
And it just so happens, the reason why you don't have to do two of them is because the temp matches the elevation data perfectly.
Right, because this is just a list of numbers. Like, okay, the first one is good, the second one's good, the third one's good. So it's a list, 1, 2, 3, 4. It might skip 7 or it might skip 8. It's going to skip all of the no datas. So, you know, it's going to skip all these red values. So if this is like the 7,000th value and this is the 7,001, then 7,000 is going to be in the index, but 7,001 is not going to be in the index. All right. So it would be great if you if you kind of dwell on that and ask me questions about that. I would encourage, if you want to ask me questions about how this part of it works, I encourage that. Okay, that's not a bad it's not wrong to ask that, and you won't receive any negative points for doing that. Okay. However, you don't actually need, in order to complete the assignment, you don't actually need to know anything besides that the X and the Y here are NumPy arrays that you will chart in your scatter plot. And so you'll need to pull in the scatter plot data. Now, one thing that I've done here is, I'll put a comment here. This code does a simple linear regression model, but does not plot. So I just put this little line of code in here because it's one line, and you can replace this with all the other code from the regression or the scatter plot.
Put in that location right where you type it.
Yeah, so basically here, this is a placeholder and this print statement. These two lines of code are a placeholder for you need to add the code that makes the scatter plot. All right? So that's a placeholder. Now let's think about what else we need to do. what else do you need to do to complete this assignment? Well, you need to build a raster where the raster is equal to that formula that's created. So I'm going to go ahead and run this really quick just to show you that it works. And hopefully it does. So these are all the previous runs of the other one. So now I ran that. Those values are totally not right. So elevation, sample.
So you're saying those two lines we can just paste over. You don't necessarily need
Right.
them.
These two lines you don't need. There's something. Something not quite right here.
Other examples, the whole, pretty much the whole end of this is this Midwest body. That's why I would imagine, especially line and next to the line, you should just go copy and paste what we did in the other example right into theoretically.
Yeah, sorry, was there a question? But I think what she's describing is right. Sounds to me what's right, because basically you're going to combine this with that other script.
And if it's that number, like 1, 2, 3, 1, 2.
Temperature array. Hold on a second here. This was working before I made the changes to it, and now those values don't seem to be right to me. So let me just download a fresh copy of the one that I uploaded before and see what change I've made really quick. So this is the final exam starter.py. File new, file. Yeah, because I tried to clear this up, and for some reason I'm just going to call this test.py. Okay, so yeah, those values are correct. You see, so for every 1 meter in elevation, I'm changing this many degrees. So what I really want you to do is express it in thousands. So I want you to take this number and multiply it by 1,000. So it'd be for every 1,000 meters in elevation, you're going down 4 degrees. But this number is totally wrong. So in my example here, I've messed something up where I took the temperature array X, good index, elevation X. It's the same thing. I'm just doing that in another step. I thought those would be equivalent.
Yeah, mine errored on that last line, the slope intercepts on our values.
I'm just wondering if this is actually reversed here. Just a second. Mine doesn't error. Mine just produces an incorrect result. Because I tried to retype the code just so that it'd be a little bit easier to understand. But in doing so, I've added some logical error that I'm just not seeing. Is this running? Yeah. The temperature should be Y, and the elevation should be X. Yeah. Okay. Well, anyway, you're not even going to use this function anyway, but now this is the right. It is producing the right number. So somehow that's just reversing that X and the Y value.
So should the
Temp.
temp be X and the Y elevation? Or do I get that backwards?
Yeah. So temperature should be Y. Let's look, because I'm using this function that I'm not as familiar with, but it says X and Y. Huh. Anyway. Yeah, maybe that function is just using X and Y different. But in order to make this code work, it should be this way, because the elevation really is X, the bottom axis. Y really is the temperature. We're trying to predict temperature based on elevation. So this is producing the right result. This value is right. That value is wrong. These values are right. It doesn't make sense to say for every 1 meter in elevation, we change the temperature goes down 202 degrees. That's like crazy, right? I mean, it's not even 202 degrees in the normal range. So anyway, you're going to replace these two lines of code, like I think is what you were saying, with basically all of these lines of code. And that will give you the scatter plot that you need. And then what else do you need to do? Well, first you need to save the scatter plot to a place that the user specifies. So you're going to have to get another parameter for that. Okay? So we'll talk about that in a second. Okay? Then what else do you need to do? You need to apply that formula and create a raster data set that takes elevation, multiplies it by the slope, and then adds the intercept, and you get a new raster data set that is the result of that. And if you do that, then you will get a data set that looks just like this data. It'll look just like these correct output sample 1, sample 2, and sample 3. Okay? And when I say looks like, it may not actually look identical because the color ramps are the same. But if you click on a few points, you'll be able to see that they're identical. Okay? And they actually don't have to be like, if your Python is rounding to like, 10 thousandths of a degree different, I'm not going to take points off for that. Okay? They should be nearly identical. By nearly identical, should be significant out to several decimal places. Yeah, did you have a question?
So those have toolbox. What's the toolbox?
Okay, so yes, you do have to create a toolbox. So let's go up here in the final exam. So what I want you to do, I'll just delete this for now because it's empty. I want you to create a toolbox, and then, well, I said I'd provide a example toolbox, so I'll do that. So we'll go new script. Okay. So you're going to have a script tool. Okay? And you're going to call your script lapse rate. make that the name and the label. Okay, and then you specify your script file. Right now, I'll just choose the file that I'm using, the starter script, but it's not hooked up yet. So that'll be under courses, SBA 11. Need to choose the script. All right, so here's the important part, the parameters. All right, now I told you that you needed to specify the study area. So the first thing you could do is just say study area. And then what data type should that be?
A layer.
Exactly. What type, feature or raster? Yep, it's going to be a feature layer. Oh, good job. All right. And then I also said that you need to specify an output location for the raster and another output location for the figure. Okay. Now you can specify those as two different. You can specify those as two different parameters, or I don't care if you say output folder and then specify an output folder. Specify a folder as the output. Okay? And then you could put both the raster and the figure there. Now, you do have to change something else up here. You have to change the direction. Remember that? To make it an output. Otherwise, the user won't be able to specify it. All right. Now, personally, though, I think it would be easier to do these as two separate things. So you could say output scatter plot, and then we're going to make this be a file that you're going to choose, and then make that an output. And then we, instead of making this output folder, we'd call it output raster. Output raster. And then instead of choosing a file, we're going to choose a raster. Okay, so a raster layer is remember, just like a feature layer, a raster layer is a representation that's already that's virtual, that's being displayed. It's actually not the data, it's the representation of the data. And so you can use a layer as input, but you can't really use a layer as output because it's a layer is built on data, and it's the symbology that's involved in that. And so you need to actually use the value itself. It needs to be a raster, not a raster layer, or it needs to be a feature class, not a feature layer. In this case, it needs to be a raster. And so you need to, it's called a raster data set is what you need to feed it. So you need to say a raster data set, and what that'll do is allow you to save it as a raster, like a file or an item in a geodatabase. Okay. Now go ahead.
You'll put something into this particular data set, right?
Right.
The data set.
Well, once I say OK here, you can see that now when I double click on this, it's asking me to choose a study area, and I can choose one from here, or I can hit the little button and navigate to a location and say I want sample 1. But with the output raster, it's going to ask me to go to a location, and I could call this, output 1, and then hit save. And now it allows me to save it there. And if I choose something that already exists, it will warn me and say, okay, well, you can do that, but you're going to overwrite that. And then finally, the output scatter plot, I would specify a location, and I could just say output.png. It has to be a PNG, by the way. So now I'll do that, and it says PNG. Now, when I run this, it's not actually going to use these parameters. That's part of what you're going to. That's part of what you're going to change in your script. Okay, when I actually run this, it is going to run my script now, but it's just going to run it again using the same values that are already in it. Here I've put the sample 1, and I'm actually not saving anything. Okay. All right. So what else do you need to do? You need to. That's actually not the one we've been going off of. Yep. So what else do you need to do? Well, here, underneath here, that's where you need to create. First of all, you need to isolate and get a variable that has the slope and the intercept in it. Once you have the slope and the intercept values, you need to run a tool that will multiply all the elevation values times the slope and then add them to the intercept to get the lapse rate value at that location.
So multiply all values by the intercept or the slope?
The slope. The slope is m in a linear function. So you multiply everything by the slope, then you add everything. So basically, I'm going to explain that here. Right here. Slope times elevation plus intercept. So this is basically a raster calculator function. You want this raster. This raster is the final product, and it is these rasters. This is the raster you should get for 1. Although I guess it deleted it in my data set. It didn't delete it online, so don't worry about it. But when I ran it, it deleted it because it was warning me that it would overwrite it. Okay. All right. So that's the final result, and it's the elevation times the slope which you derived plus the intercept which you derived in your data. Okay. So I'm already printing out, in my scatter example, m is the slope and b is the intercept. So you're already getting those values. After you run polyfit, you're getting m and you're getting b. Or, if you want to leave the code the same way it is, you're getting the slope and the intercept here. Well, I'm calling them slope and intercept here. But you don't really need any of these other values, the R value, the P value, the standard error. We didn't even really explain what those are, but they talk about how well that line fit. Okay. Well, the R value is actually the correlation coefficient squared. So we didn't talk about that one. But we didn't talk about the P value of the standard error.
So you don't know if all you need is the slope, the intersection, and whatever. Or the second line, slope, intersection.
Right. So you need. This is going to be total pseudocode, but your output raster will equal the slope times the elevation raster plus the intercept. Okay, so you need to figure out how to code this. Okay, we've done it in the past. You could do it in 2 steps. You could do the elevation times the slope. That's actually done up here. So you could just recreate this line and say the new raster is equal to arcpy.sa.times elevation, comma, instead of 1, you would do this value, whatever's in slope.
Could you just put slope,
Yes,
essentially?
exactly. That's exactly what you're supposed to be learning, is that slope contains a variable that holds a value, and you're trying to put that in there. Yep, that's what's being tested. So and that's exactly right. All right, so once you do that, all you need to do is save that raster out into the location that the user specified. So if you don't know how to do that, that's all in get parameter as text. I'll give you another hint. You don't have to use set parameter as text in this. There's no reason to do that in this assignment. But you are going to use get parameter as text. So you're going to get all 3 of the parameters the user entered. The user entered the location of the study area. They entered the location that they want to save the raster out to, and they entered the location where they want to save the image, the plot image out to. They want to save all 3 of those out onto disk. No, sorry, the last 2 out onto disk. And so you need to get those. Sorry, go ahead.
So that's what you would use to get parameter as text for?
Yep, and then they become a variable, and those variables you just need to feed into the right places. So go back and look at examples of saving a raster into a certain location. Remember we did raster.save and different labs, and then we have an example of saving the figure out in today's material.
So you said we need 3 parameters for them to set?
Yeah. Well, yeah. I think the best way would be 3. I said, well, as I was making it, I said you could just specify the folder and they put the raster and the scatter plot in the same folder, but let's just do it this way. I'm going to upload this toolbox so you'll have it, but
okay, but that's not in the example as far as like it's already set needs.
well, I talk about it.
Oh, okay, it's down here.
Yeah. Okay, so as far as grading, I'm going to be a little bit more methodical on the grading this time. So I came up with some ways to do that. Basically, if your tool works and you get the results that I've already shown you the results, what they should look like. If you get those 3 results from those 3 data sets and it works, you'll get an 85 out of 100, which is a B, right? So you get a B if it works. So if your scatter plot is written out to a file in the code, you get an extra 4 points for that. If you'll get 2 points for writing the correlation coefficient and the actual lapse rate. It needs to be the slope times 1,000, not just the raw slope value. If you write those out into the processing window as a message, so go back, you answer this question, how do we write messages to the processing window instead of printing them? Do you remember talking about that earlier in the semester?
This book I have, but I don't remember off the top of my head.
It's not in the book. We talked about it earlier in the semester.
Well, this book Maggie gave me to use.
Oh, okay.
It's a little different than the book.
Okay, so look, I could just write arcpy write message to processing window. Writing messages in script tools. You guys remember talking about add message? So that's how you're going to do it. You get 2 points for adding it. So go read about that and do that. All right, so that's the add message function. You get 4 points for styling your code. In other words, this one might be a little bit difficult. It is going to be difficult because it's going to involve rearranging how the code's written. Honestly, the way I have it set up right now, except for the last part where you write the 2 or 3 lines of code that make the output raster, besides that part, this is a cut and paste exercise, right? You just take what I've already written, you cut and paste the linear regression part from the scatter plot, cut that over there, and you'll get a scatter plot, and then you write the part in the end about multiplying it by a raster, okay? And you're done. Well, you have to turn it into a toolbox, which is also, there's some skill involved in that, but you can do that. Okay, so besides that, it's pretty easy. However, to get these 4 points, you're going to have to restyle your code, and you're going to have to create a function, and your function takes the path to the feature class and the path to the output raster. And so most of the code will then run inside of a function, and you'll call that function once. So if you want to go for this, I would recommend getting it working and then reworking your code so that it runs as a function. So you'll have a function that'll be called create raster, and you'll just pass those 2 values, the path and the path to the input and the path to the output, and then it'll actually run all of that inside of a function. All right, so
that was for extra points, or is that?
Well, those are for points beyond 85. That makes sense?
Okay.
So in other words, like you can still get an A if you didn't do that, but you print the scatter plot out to a file. You added 2 points for you did the correlation coefficient. You add the messages. Now we're up to 6, so you're at a 91 already. Okay. So you don't have to do that, but you could. Right? You get 1 point if your solution's turned in before midnight on December 15th. So basically, if you turn it in a day early, you get a point. Well, yeah. And so you get up to 2 points. So you get 1 point if it's turned in on the 5th, and you get an additional point if it's turned in on the 6th. The 6th is the actual due date. So if you turn it in before the 6th, you can earn up to 2 points. Okay? Again, you don't have to, but you can. And what I'm going to do is encourage everybody to turn in what they have on the 5th or the 6th so that you can get some feedback like last time. Because remember last time, I actually said, okay, well, you didn't do this right, you didn't do that right, and I gave it back to you. So I'm going to do the same thing, but it's structured a little differently. So it's basically, I've come up with an actual, like last time I said you're not going to get full credit back. Now I've specified exactly what that means here. So, all right. So then the last time, maybe I should have put this up before this, but you get 3 points for correctly inferring which of the 3 sample areas has the highest humidity. Because remember, humidity, if we go back to the beginning of class, humidity is the major determining factor on why lapse rates differ. So just put a statement that says area 1, area 2, or area 3 has the highest humidity, and why you think that's the case.
Like a statement in the code, or just like on the little note box when we
Yeah,
turn
just
it in?
either way. Just
Okay.
send. Yeah, I would put it in a note box. Yeah, put it in a note when you turn it in. Which one has the highest humidity, and why that's the case. I don't want to hear a physical answer. Like I don't want to hear if area 3 has the highest. I don't want to. Well, that area has the highest humidity. I know because I've been there, and man, it's humid. Like that's not what I want to hear. What I want to hear is that that area has the highest humidity because it has these numbers. In other words, the slope of that line is this, which means, since we already know that humidity is the other variable that's explaining it here, you don't have to say all this. But it's because of the number, and that number being high or low. That's what your answer needs to contain. In other words, if the slope is really high, it means something, or if the slope is really low, it means something. All right, so if you turn in an assignment early or on the day of, you get for turning it in the day it's due, you get 1 point. For turning it in 2 days early, you get 2 points, basically, is the way that works out. Because 1 for 1, the 5th or the 6th. You're not going to get credit for turning the assignment in early unless it's correct. So you're not going to get those points. So just like on the midterm, you're still not going to get full credit if it's not turned in by the 6th. But what's going to happen is I'll be able to respond back and tell you what's wrong, and I'll do that fairly quick. What's going to happen is for each day passed, starting if you turn it immediately back in on the 7th, you're just 1 point off, and then 2 points off, 3 points, all the way to the 13th. So on the 13th, you get a total of 7 points off if you turned it in. I have to turn grades in the next Monday, so it needs to be in by the 13th. So that's going to drop you down as much as almost a letter grade. Could be, could not be, if you don't turn it in on time or if you have to rework it. Okay. All right. So then you can turn your script in not built as a tool, but it won't count as being early in that case. And in addition to that, if it's not built into a tool, that's an automatic 10 points off. It needs to be built into a tool. So that is full letter grade lower.
Okay, now, you will see how you built that toolbox when you explained it to us. That wasn't built into Python. You actually built it from Art Pro, right? You went into Art Pro boxes.
Yeah, that's exactly what I'm talking about. You need to go into Arc Pro, make it a toolbox, and then turn in the script and the tool.
Okay.
Yep. So you do need to do one part of this assignment in ArcGIS Pro. You're getting ArcGIS Pro to talk to your script.
Okay.
Exactly.
Once you build your script, you can just copy it into your tool, the script box where the tool's at, and then you should be able to just edit it to line up and then go.
Yeah, I would suggest building your tool, getting it working as a script tool. As a script, sorry, and then isolate at the top. You're going to isolate your input parameters, which I've already done for you for 2 of them, and then all you have to do is change these lines of code to arcpy.getParameter as text 0, 1, and 2, and then your script tool should work. See what I'm saying?
Yep.
Okay. All right. So then I'm giving myself a fair bit of leeway here, but I tried to describe it a little bit more. So you can get up to 30 points off for turning in an incorrect solution. Okay. So 5 points will be reduced for a solution that executes but has minor logical errors, including ones where you even get the right answer, but you're still technically doing something wrong. You could, you could hard code in script area 1, 2, or 3, and run it 3 times and get the 3 correct answers. But I specifically said you can't hard code in the study areas. So that would be an example of you still got the right answer, but you didn't build a proper script tool. Okay, so that's 5 points off. 15 points off for a solution that executes but it's still missing a major component of logic and therefore produces an inaccurate solution. So I could see maybe somebody reversing the x and the y's, or they might do the formula wrong. They might reverse slope and intercept. They could have a rounding error somewhere. I don't know for sure if that comes into play, but it probably could when you do the multiplying of the final raster back out. Or they just leave off a whole step in the processing. Okay. I'm going to get marked off for that. And then 30 points off for a partial solution that doesn't work or entirely leaves off most of the logic necessary to complete the assignment. So if you make a hardy attempt that doesn't really do any of what I ask, but you zip up something and turn it in, then you would fall into that category, which 85 minus 30 would be 55. So that'd be a failing grade. So hopefully you don't fall into that category. All right. So that's what I came up with for kind of like a rubric for a programming assignment. Okay. So anybody have any questions about that?
So when you say for the second on the for getting points, when it says 2 points for writing the correlation coefficient, the actual wax rate, so you're just pretty much the output, like with the plot, you want it to be an actual, not like 0.0046. You want it to be an actual like 4,000 or 4 degrees or whatever.
Yeah, it'll be 4 degrees for that study area 1. Negative 4 degrees.
Yeah.
Yep. And so they need to be in the output window. Now the plot can't go in that window. It won't put that plot in that window, but you can get the correlation coefficient and the lapse rate. It'd be helpful if you wrote the correlation coefficient is this and the lapse rate is this, not just put those numbers there.
And that's been like the message back.
Yeah, so when I run a tool in ArcGIS Pro, if I go back to history here. So these are the messages that ran when that tool ran. Right now there's nothing, but after running I should see, either one line with 2 values on it or 2 lines in between the word running and the word complete. Yeah. So here's the starter for exam 1. So if I did arcpy.add message, right. So now it says hello. Okay.
Does it matter where you put that in your script? Can it go like at the very beginning or the very bottom? Does it matter?
Well, since you're reporting the correlation coefficient and the lapse rate, it needs to be after you have those values to report. But other than that, it doesn't matter where it is.
And then the output raster is actually that's gonna be our lapse rate raster, correct?
Right. You're gonna create that raster. You're gonna create that.
Yeah.
There is a way to do it all on one line of code like this, but you could do it in 2 lines of code. You could run arcpy.sa.times and then run arcpy.sa.plus. and then you're going to need to run you're going to need to do raster.save, like we did when we covered rasters a few weeks ago. So let's see if there's an example. So by default, when you run a raster tool, it creates an in-memory raster. And so to save it, you have to say raster.save. See if they're.
That's on the output raster. That would make.
Yep. Yep. So you know, if you ran it like this, you'd have output raster.save path to raster, something like that. All right. Any other questions?
Okay, now path to what raster?
The raster that you create.
Okay, path to the output raster.
Mm-hmm.
Yeah, the output raster that was created.
Now the output raster, they are telling you where to save it. The toolbox will tell you where to save it, and it's that path.
The correlation coefficient is just that slope, right?
No, the correlation coefficient isn't actually calculated here.
Okay.
It will be in the cut and paste job that you do.
Okay.
Okay.
The square root of the R value will be the correlation coefficient unsigned. So technically you could say R value, you could get the I forgot whether. Yep. Okay. That'll work in Python. Oh, no. Yeah, it's just a double. So, so this will give you the square root, and then you could say. But the easiest way to do it is just to cut and paste it. But so the slope will always have the same sign as the correlation coefficient. So what you could do is say slope. How could you get the sign of the slope? Times the slope. Oh yeah. I don't know how to do it without an if statement. Like you could just say if slope is greater than 0, sine is equal to 1, else sine is equal to -1.
Yeah, but the cut and paste job has a correlation.
Yes, it already does, exactly.
Okay.
So that's the way I would, you know, that you could get the correlation coefficient by doing that. So you're getting the square root of the R value, which will always be positive, right? Because this R value is always going to be positive. Because if the correlation coefficient is negative, the definition of the R value is it's the square of the correlation coefficient, so it's always going to be a positive value. So in order to rebuild the correlation coefficient, you need to take the square root and then multiply it by the sign. So anyway, yeah, I'm going to take that out because I think it's going to confuse people. But that's that. Right. Okay. The second question is a little bit more straightforward, and so let's talk about it after a break. So let's come back at 2:35, unless there's any more questions right now.
I think I asked all I can.
You asked a lot of great questions. I appreciate you asking them. All right, so